So, if you've ever sat through a calculus class, you probably spent a lot of time learning how to find the rate of change for these perfect, clean functions. But what happens when you leave the textbook behind and step into the messy, real world? Well, that's what we're going to get into today. We're looking at how computers handle calculus when the data is anything but perfect, using a super powerful set of tools called numerical differentiation. Let's start with a real-world puzzle. Imagine your car's computer gets a speed reading every single second, 10 meters per second, then 12, then maybe 14.5. Now, you know from physics that acceleration is just the rate of change of your speed, but you don't have a nice smooth curve here. You just have these little snapshots in time. So how in the world do you figure out the acceleration at exactly the halfway point between two of those readings? This isn't just a thought experiment. It's the kind of problem engineers and scientists have to solve every single day. And that car example, it really gets to the heart of the issue. Classic calculus is absolutely brilliant for a function you can write down, like y equals x squared. You can find the exact derivative pretty much anywhere. But real-world data? It doesn't come in a neat little formula. Data from sensors, from scientific experiments, or from the stock market, it's just a series of separate, discrete, and often kind of noisy data points. Okay, so since that real-world data is so messy, finding the one single exact answer is pretty much impossible. So what do? We do the next best thing. We get clever and we estimate it. Instead of trying to find that perfect tangent line at a single point, we just use the points we actually have, its neighbors, to make a really, really good educated guess. And this brings us to the official name for this whole idea. Numerical differentiation isn't just one magic trick. It's a whole family of techniques. And they're all designed for this one specific purpose, to estimate a derivative, that rate of change, when all you have to work with are those scattered data points. At the end of the day, the principle behind all of this is incredibly simple. You want to know the slope at one specific spot, but you don't know the exact curve it's on. No problem. You just pick another point nearby that you do know, draw a straight line between the two, and calculate the slope of that line. Yeah, it's an approximation, but as we're about to see, it can be a shockingly good one. So how we choose which neighbor to connect that line to, well, that leads us to a few different methods, and each one has its own set of strengths and weaknesses. So let's pop open the toolbox and take a quick tour of the 3 most common tools you'll find. First up, we've got the forward difference. This is probably the most intuitive way to do it. To get the slope at your point x, you just look at the very next point you have, x plus h. Then you find the change in the value, the rise, and divide by the distance between them, the run. It's literally just the classic rise over run you learned back in algebra. Simple, direct, and super easy to calculate. Now, the big plus here is obviously simplicity, but there's another huge advantage. Since you're only looking forward, it's perfect for the very first point in your data set, where you have no past data to look back on. But there's a catch. It's not the most accurate method, and it has this built-in bias because it completely ignores everything that's happening on the other side of your point. And as you can probably guess, the backward difference is just the mirror image of that. To find the slope at point x, you look at the point that came right before it, x minus h. It has basically the same pros and cons as the forward method, just in reverse. This makes it really useful for the very last point in your data, but it's still just as biased. Okay, but what if we tried to combine these two ideas? Well, that brings us to the central difference method. And honestly, this is a huge leap forward. Instead of just looking in one direction, it looks at both neighbors, the point ahead and the point behind. And take a look at the formula. We're finding the difference between the forward point and the backward point. And then we divide by the total distance between them, which you'll notice is 2h. So why is this one so much better? It's all about symmetry. By taking information from both sides, those little errors and biases that we saw in the forward and backward methods, well, they tend to cancel each other out. And the result is a dramatically more accurate estimate. The only real trade-off is that you can't use it at the absolute edges of your data because, you need a neighbor on both sides. This brings us to a really crucial balancing act that you see in pretty much all of numerical computing. The classic trade-off between how accurate you want your answer to be and what it costs to get it. So let's put these methods head to head. Okay, so the crucial point is hiding right here. Look at that accuracy order column. You see those OH and OH squared things? You can just think of this big O notation as a rating for how quickly the error disappears as your data points get closer together. For OH, if you cut your step size h in half, your error also gets cut in half. That's pretty good. But for OH squared, If you cut h in half, the error gets 4 times smaller. It gets better, much, much faster. And you don't even need the math to see the difference. Just look at this chart. For the exact same data, the error from the central difference method is just in a completely different league. That whole OH squared thing isn't just some dusty academic detail. It makes a massive, practical difference in getting a reliable answer you can actually trust.
All right, so we've got these different tools in our toolbox. How do we know which one to actually pull out and use in the real world?
Well, for the vast, vast majority of applications, the answer is actually really clear. The central difference method just hits that perfect sweet spot. It gives you a huge jump in accuracy compared to the simpler methods, but without getting crazy complicated or computationally expensive. It's the reliable workhorse of the bunch. And hey, this isn't just theory. If you've ever used the super popular Python library NumPy for data science, its main function for calculating gradients, numpy.gradient, it uses the central difference method for all the interior points in your data by default. It only falls back to those less accurate forward and backward methods right at the absolute edges, where it has no other choice. This stuff is out there, being used right now.
Now, before you go and start applying this everywhere, there are a few really important warnings. First, let's talk about noise. Real data is messy, and these methods can sometimes accidentally make that noise look like a real change, so you often have to smooth your data out first. Second, and this one's a little weird, is something called round-off error. You'd think that making your step size h as tiny as possible would always be better, right? Well, because of the way computers store numbers, going too small can actually make your answer get worse. And finally, just know that this isn't the end of the road. For fields like aerospace engineering, where you need insane precision, there are even more advanced higher-order methods that use 5 or even 7 points to get an even better estimate. So we're left with this really cool thought. The elegant, perfect world of textbook calculus needs these clever, practical workarounds to even function in our messy, data point reality. And it makes you wonder, where else are these hidden approximations at work? From the way we forecast the weather to the physics in a video game, they are absolutely everywhere, silently translating the perfect language of math into the practical results we rely on every single day.